So as I was saying in the end of the last video, there's two different ways of starting this problem. We can either start by using the property that allows us to take this -3 and displace it into both parts of this quotient, or we can simplify the quotient first. I want to simplify the quotient first because it'll give me one less step as I go on. I'm thinking if I do these two things, I'll still have to simplify it. So if I simplify it once, I'll have one less thing to do. So that's my choice, but either way is going to work. So go ahead, I'm going to simplify this first. It's x to the 4th over x squared. So subtracting those gives me x squared over 1, or just x squared, to the -3rd. Okay, and x squared to the -3rd. Multiply those together, x to the -6th. And then finally, that needs to be rewritten so that x to the 6th is in the denominator to make that have a positive power. Alright, let's move on to the next two here. Alright, as this parenthesis on the bottom here is just on the y to the 4 squared, I'm going to do that first. So I'm going to have y to the -3 over y to the 2 times 4 is 8. Next I'm going to say, I'm going to go ahead and move this down because it has a negative power. So it's 1 over y to the 8th times y to the positive 3rd now, and add those powers up. Okay, so I'm going to have y to the 11th as my final answer. And again, there's more than one way I could have done this. I do want to do those parentheses first, just kind of following order operations. If I have a set of parentheses like that, I'll take care of them first. And then I could have subtracted these or move them around in a different way first, but that was my choice. I was saying I'm going to get rid of that negative, and then I can see that I want to add those up. Okay. In the next one, let's look at this fraction. Those can be reduced. Divided by 7 is going to be 2/3. The b's, okay, let me just go ahead and rearrange things. There's a lot of stuff up there, so let me just make all the powers positive. So it's going to be b to the 4th, still positive. B squared's moving up. C to the 3rd's moving up, and C to the 7th's moving down. Okay, so let's keep working on it right here. The B's are going to add up because you're both on the top now, and the C's are going to subtract because one's on top, one's on bottom. More C in the bottom, so when I finish the subtraction, the result's going to stay on the bottom as a positive number, right? 7 minus 3 is 4, stays in the bottom. Okay, let's check out the next page. Alright, this is our scientific notation page. A number is written in scientific notation if it has the form a times 10 to the n, where n is an integer and a is a value between 1 and 10. Okay, so for example, 1 times 10 to the 8th is in scientific notation, or 2.49 times 10 to the -13th is in scientific notation, but 21.5 times 10 to the -4th is not in scientific notation because that's too large. If I wanted to write in scientific notation, I have to make sure it was like 2.15 times 10 to the -3rd or something like this. So let's go ahead and look at some of these examples here. We've got a reference chart over here for just names of large numbers. You know, if I have 10 to the 8th, what's it really called? Well, that's not on the chart, but 10 to the 9th is a billion. So 10 to the 8th would be 100 million, one power less than a billion. Okay, so if I have 10 to the 27th, it's an octillion. So you can just see the different names here in case you're curious and you see large values. Okay, so writing a number in standard decimal notation. Okay, so in standard decimal notation, when I multiply by 10 to the 3rd, that's going to make the decimal place move 3 places to the right, making the number larger. This is going to be 5, 1, 2, 3 places, putting it over here. So it would be 5,300. And this makes a bit of sense if we notice that 10 to the 3rd is supposed to represent thousands. So 5.3 thousand is 5,300. Okay. And same thing on this one. We're going to move it 6 places to the right since it's a positive value for the exponent. The positive values are going to make this number larger, so they're going to go to the right. So this is going to be 8 was already there, that doesn't count, and then 1, 2, 3 places, 4, 5, 6. Okay, so it used to be here, and it moved 1, 2, 3, 4, 5, 6 places to the end here, and hopefully that's going to make a bit of sense. 6 is supposed to be million, so this looks like 8,192,000. That would be the name for this number. Okay, vice versa, if it's a negative exponent, we're moving to the left 3 places. So I'm going to start with 0 point, then I have 1, 2, and the third place is that 4, 6. So you can see that from where it used to be, the decimal place has moved 1, 2, 3 places to the left. Left because the power was negative. Again, here the power is negative, so I'm going to move the decimal place to the left, making this number smaller. So 0.1, 2, 3, 4, and the fifth one's at 2, so 5, 9, 9. Okay, so from between the 2 and the 9, the decimal place moved 1, 2, 3, 4, 5 places to write this number in standard notation. When they're written all the way out, that's standard notation as opposed to the scientific notation here. Okay. Objective 4 is converting a number from regular standard decimal back into scientific notation. Okay. So when I'm looking at this very large number here, remember that scientific notation should be one single digit, then my decimal place. One single digit, my decimal place, and any other digits that appear. So I'm going to write the first digit, which in this number is 3, 0.6. I don't want to write all the zeros. There are no other numbers. If this would have been a 1, I'd do 601, and then I would stop because the rest of it is zeros. So those are the only two significant digits. So I'm going to write those like 3.6 times 10 to the, and now I got to count how many places I just took off. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I took off 9 decimal places. The next question is it a positive 9 or is it a negative 9? Okay, it's going to be a positive 9 because I need this number right here to become larger to get back to the original. So if I wanted to rewrite it, it would need to move to the right in the direction of large numbers, so it needs to be a positive 9. So the same thing in this one here. Ignore the zeros. This would be 4.7 times 10 to the, getting rid of 1, 2, 3, 4, 5, 6 zeros, but that would just put it in front of the 4, so I've got to go one more to go after the 4, 7. And that's going to be a negative 7 because I've made this number a lot larger than it really is. This needs to go, when I'm drawing that arrow, I'm drawing it based off of my scientific notation value. My scientific notation value's got to go to the left to get back to the original standard value. Okay. Alright, so what does scientific notation have to do with exponents anyway? In our note. If you are looking at your calculator, most calculators represent something like this, like 7.29 times 10 to the 26th. They represent it with an E. So if you have a number that ever shows up with E26 on the end right there, it's in scientific notation and it would mean the same thing as this. Okay, and that happens sometimes if you have very large or very small values. Okay. Now back to our exponents in scientific notation. When I'm multiplying two numbers that are in scientific notation together, I multiply the values together, A times B, times 10 to the, well, if I have two different exponential expressions multiplied together, we know that we add the exponents. Same thing for division. Divide the numbers, and then if you have two different exponent expressions divided, you subtract the exponents. And if you have exponentiation, if you have a number to a power times an exponent to a power, you're going to multiply those exponents. So let's look at the examples here. Alright, 2 times 10 to the third times 3 times 10 squared. I know that 2 times 3 is 6 times 10 to the 3 and 2 is 5, adding those exponents up. Okay, division here, 5 into 15 is 3. What to do with the exponents? Times 10 to the, okay, so imagine moving that 4 down here, because it was negative, and then that's going to be 10 to the 6th in the bottom. I can't write bottom with scientific notation though, so it's the one time where I'm going to need to use negative exponents. So 1 over 10 to the 6th is the same thing as 10 to the negative 6th. Okay? So normally we don't want to leave something with a negative exponent, but in scientific notation, that is the way it must be. Alright, and our next one here, let's see. 3 to the 4th times 10 to the, let's multiply those together, negative 8th. 3 to the 4th is 81 times 10 to the negative 8th. Now we have a problem because 81 is not in scientific notation. I need to change this to 8.1, but how is that going to affect my exponent? Okay, so 8.1, let's think about this for a second. This number right now was 81 with the decimal place moved over this way 8 times. If it's 8.1, the decimal place needs to be moved over 1 fewer time because it's already moved 1 time. So 1 fewer time would make this decimal be negative 7. 1 fewer movement. Okay, and let's just say that one more way to see if that makes sense again. I made this number smaller, right? 8.1 is smaller, so I'm going to do the opposite over here. We made the exponent larger. Negative 7 is larger than negative 8. Okay, so you can think about it in terms of, I would have had to have moved it 8 places. Well, it's already moved 1, so I only have to move it 7 more. That might be a good way of thinking about it. Or if this number, 81, turned into a smaller number, this exponent turns into a larger number to compensate. So I can't leave it as 81 times 10 to the negative 8. That is not in scientific notation. It needs to be 8.1 times 10 to the negative 7th. Alright, and we've got 2 more examples here. If there are approximately 3.2 times 10 to the 7 seconds in a year, approximately how many years is in 1.35 trillion seconds? I need to look up trillion. Trillion is 10 to the 12th. Okay, so let's go back. Trillion is times 10 to the 12th. We're going to do a little unit analysis on here. That's in seconds. And there are approximately 3.2 times 10 to the 7 seconds in 1 year. Okay, that's going to help seconds cancel. And it's going to turn it into years. Okay, so we're actually dividing these two numbers. I need to grab a calculator. 1.35 divided by 3.2, 0.42, 0.421875 times 10 to the, I'm going to subtract those powers, so 10 to the 5th, but that's not in scientific notation, so you need to write this as 4.21875 times 10 to the, I made that number bigger, so I need to make the power smaller. Okay, so 135 trillion seconds is about 4.2 times 10 to the 4th years.